Welcome back to the second lesson on Unit 9, Electricity, where we're going to talk about electric current. So first, I want you to think of current as the flow of specifically positive charges. And the positive charges are always going to flow from a high potential to a low potential. So think about water flowing from a high elevation, from a high height, to a lower elevation. Water always flows downhill. It's the exact same with charges. They're always going to flow downhill, or from your higher voltage to your lower voltage. In other words, down the electric potential difference. So that's huge. The flow of positive charges, that is your current. And it's always going to go from a higher voltage to a lower voltage. So first, we just need to take a second to stop and think, what do you believe is moving in a wire that conducts electricity? Well, probably, based on the last unit that we did, electrostatics, and what you know about moving charges, you should answer this and say, hey, the electrons are the things that are moving. That's what's mobile within the wire, creating a current. Well, this is interesting because electrons are actually going to be going the opposite direction that we've defined current, because current is the flow of positive charges. So that gives us a pretty significant takeaway. If you're wondering, why does it have to be that way? Why is current the opposite direction of the way electrons flow? Think back to Ben Franklin. He's the guy who started this. We've just kind of used his standard for the flow of positive charges. Since then, he identified current, he defined current that way. But if you want to read a little bit more about him, go ahead. But for his reason, for that sake, current, which is a flow from high to low potential difference, that's the direction the current's going to flow. Think of high being your positive and low being your negative. Electrons are going to flow the exact opposite. So they're going to flow from low to high, since they're the flow of negative charges, from the negative to the positive side. A little tricky, but remember that current is a flow of positive charge. That's just how we define it. Now, mathematically, if you take a look in your reference table, you can see that current, which is represented conveniently by the symbol I, is a change in charge over time. So let's just quickly define these terms. Q is charge, and we measure charge in coulombs. T stands for time, which we measure in seconds. And then don't forget that a change is just a final minus an initial, so a difference. So if we want to take a look at units real quick, you know that charge is a coulomb and time is in seconds. Current is effectively the movement of charge per second, which we give another name. We call it the ampere, which we can abbreviate, and you've probably heard as amp, which we can also abbreviate and just use a big capital A. Now, similarly to electric potential difference, don't confuse your unit and your symbol. Current, with the unit I, that's what we're talking about. Current is a movement of those positive charges. The unit that we use to measure current is the amp. Two different things, current versus the amp, the variable versus the unit. So now let's do a quick example. Current, we know we want a charge of 30 coulombs to pass through a 24 ohm resistor. So you might be thinking to yourself, what is that? We haven't talked about it yet. That's fine. This is extra information. Sometimes they throw that at you to keep you on your toes. In 6 seconds, we want to know what's the current through the resistor. So I'm going to set up my equation. I equals the change in Q over time. And I know that our change in Q here is going to be 30 coulombs. And the amount of time is 6.0 seconds. So I do a quick bit of division, and I get 15 coulombs per second, which I know is the same thing. I'm sorry, not 15. That math, 5 coulombs per second, which I know is the same thing as 5 amps. And that will give you my current. Let's just do one more example. We're looking for we're looking for the charge this time. This time we'll give it the current, 2.0 amperes. And I want to know how many coulombs of electric charge pass through the light bulb in 1 minute. So I've got I equals the change in Q over T. I know that the current here is 2.0 amps. I'm looking for the change in Q And I'm giving the time, which is 1 minute. However, in order to keep our units consistent, we need to convert to seconds. So this is 60 seconds as our time. I'm going to do a little bit of cross multiplication here. If you put this in your calculator, you get 120 coulombs is equal to the change in Q.